Hello everyone and welcome to my Kawaii SX240 repair video. It's not going to be a restoration this time, it's just a repair for a friend, so I won't be pulling it all apart and cleaning it and replacing all the buttons, all that kind of stuff. In fact, when I first started the repair, I realized it was just a battery leak on the main board, and I thought that wasn't very interesting to make a video out of. But when I started repairing the board, I was reminded of a whole lot of posts on the internet where people were struggling with how to clean up battery leaks and what was even coming out of the battery and that kind of stuff. So I thought, wouldn't it be great if we had a video that went through all the different types of batteries that you can find in synthesizers and what leaks out of them and how to clean them up. So I thought, well, I better pull out the camera then. And here we are. So I think I should be able to do this quite well. I'd studied chemistry and electronics. I started off working in a lab and thought, I got bored really. So I went back and did electronics. Now I repair the large equipment in laboratories. So my life's electronics now, but I reckon I can do a pretty good job of this. So I hope you enjoy it and get something out of it. Okay, so what types of batteries do we find in old analog synthesizers? Well, the most common would have to be probably the general purpose and the heavy duty. They were the most available at the time. And you'll find particularly the AA ones in the first Yamahas to have patch memory and the TR-808. Then Roland started using larger ones for the portable stuff like the 606 and 303. You'll find the C-size ones. The general purpose and the heavy duty are slightly different. The electrolyte's different. Apart from that, they're basically the same. You can consider them an acid battery. What leaks out of them does accept an electron, therefore freeing up a proton to act like acid, and they will rust a lot of metals. They're quite hard to get off. You may find some alkalines as well. Obviously not an acid. It's written on the battery that it's alkaline. So these will be most likely potassium hydroxide as the electrolyte, although once they leak you tend to get more of a potassium carbonate forming because it reacts with CO2 in air. And then we've got the first rechargeable batteries. You won't find batteries like lead acid batteries in synths. They were just too heavy, not as efficient. I've included the nickel metal hydrides here, even though you won't find them in synths, because they're so similar to nickel cadmium. Basically just the negative electrode's different. It's not cadmium, it's an alloy. Apart from that, they're nearly the same. And then we moved on and static RAM chips got less and less power hungry. And we could use smaller batteries to help save the patch memory in synthesizers, so that you'll see more and more button cells appear. So here's a table that I made that describes what's happening inside the batteries. The most important part to us is the electrolyte. We need to know what's going to leak out of the battery. But in some cases it's not as simple as that, because what leaks out may not be in its original form, and then it may react into something else completely different. So in zinc carbon, in the general purpose and the heavy duty, the electrolyte's different. In the general purpose, it's mostly ammonium chloride. You can have a little bit of zinc chloride added as well. But the problem here is that even though we know that the electrolyte is an acid, the electrolyte itself takes part in the reaction. So as the battery discharges and the zinc's used up, so the actual zinc in the outer casing is eaten away. It turns into zinc oxide. Part of that reaction is the electrolyte is changing as well. So the electrolyte in the general purpose is changing from ammonium chloride, which is an acid, to this ammonium zinc chloride. I can't even pronounce it. It's a difficult compound, but it's not an acid. And then this reaction isn't final either. So when we have a leak of this battery type, there's no point trying to neutralize it, because it's not in its original form anyway, and there's lots of other reactions that are happening. And the best thing is just try and get it off. The problem though is that it'll cause a lot of rust. There's lots of rust that these batteries cause. So I usually, when I come across them in 606s and 303s and stuff like that, I just try and replace the battery terminals, and then just inside on the circuit board try and replace as much as I can. So just removal is the best way, and I have been able to get some of the iron stains off the inside of the cover, because these compounds itself aren't too much of a problem. It's that kind of browny red leftover gunk that what happens when the battery terminals rust. I've gotten that off with water and a toothbrush and lots of scrubbing and that kind of stuff. You can get a little bit of it off. It looks a little bit better. But that's a real pain. It's probably the hardest one to fix. Lately, though, I've been doing a lot of NiCads. And the NiCads are different. The potassium hydroxide does come out. There's quite a lot of it. It tends to eat away at the solder mask and make things sticky, and it'll take the printing off the chips and stuff like that. But the potassium hydroxide doesn't take part in the reaction like the zinc chloride and the ammonium chloride do. So this never changes. You'll always get potassium hydroxide coming out of a NiCad battery, no matter what the state of charge is. So we know this is a base. And when this battery leaks, we will always get a base coming out. Good thing is, though, potassium hydroxide doesn't really react with metals, particularly metals like copper. You won't find it reacting with the tracks on the circuit board. You will find some reactions, though, and it does eat away at things like maybe resistor legs and some chip legs. But I don't think it's the potassium hydroxide that's doing that. The potassium is just too reactive. It's going to hold on to its hydroxide. It's not going to want to swap it with anything. I think part of the problem with the damage that we see in NiCads is more to do with the cadmium or the nickel coming out. And I'll show you that on this board that I'm repairing now. Okay, so this one's not too bad. There's not that much damage really. Here's the original battery, which sat here. So you can see the blast zone extends to about here, like this, and a little bit behind it. So it must have been around this corner that burst open. This is actually a replacement battery that someone else has put on, but it's already flat and it's completely dead at 0 volts. So that's beyond repair. What I've always found interesting about leaks is that not everything rusts. That tells me something, in that these metals that make up the legs of the ICs and the capacitors and the resistors, they're probably all made of different things. So I did some research, and indeed they are. So the legs that the ICs are made out of are completely different to the legs that the resistors are made out of, which are completely different to what the capacitors are made out of. So what we've got is a whole lot of different metals here, and only some of those metals are reacting with what's coming out of the battery. So here's my theory about what's going on. I'm going to try and do it as quick as I can, because when I originally filmed the video, I spent lots and lots of time explaining the metals in the ICs and the resistors and stuff, and the reactions in the battery and the electrochemical series, and put it all together, and it was really, really brilliant and really, really long. And when I played it back, I fell asleep. So I don't want that to happen to you, so we're going to do it really, really quickly this time. Now, the IC legs that I've got, I think, are the ones that are mostly made of copper. The way to tell is when you pull an old IC out of the board, if you snap the leg off and look down the end of the leg, the inside looks like copper. The tracks are copper. We've got some problem because our resistors, they're probably steel, which is mostly iron, and that will rust. And when I first pulled this board out of the synth, the iron rust on the legs was just unbelievable. There were some resistors that had no legs left at all. So I think it's iron that's the problem. If we have a look in the battery here, we've got not much of an issue when the battery's charged, but when it's discharged, we get a lot of ions coming out. So these hydroxyl ions, there's nickel, there's cadmium, and there's potassium hydroxide that's always there in the electrolyte. We will always get a little bit of nickel and cadmium hydroxide coming out, but mostly when the battery's discharged. when it's mostly charged, it'll be mostly on this side of reaction. So the ones we've got to watch here are the ions. And the reason why that's important is the electrochemical series. Now, if you want to know more about this, just Google it, because otherwise I will make you fall asleep. So solids on this side and ions on this side. If that's the case, we have a reaction. Any other combination, and we don't. So if we have a look at what's in our board, we've got iron, definitely lots of iron in our legs, resistors and stuff. We've got some tin, and we've got some copper. The tin's in alloys. The lead's in the solder, so we've got lead solder. And now the ions from our batteries, which I will do in pink. We have potassium, which is way down here, and that's very important. I'll tell you in a minute. And nickel and cadmium. Nickel here, cadmium here. Now, this is where it can get a little bit confusing, because we've got iron, the solid metal, on the left-hand side, and we've got two hydroxyl ions on the right-hand side, so nickel and cadmium. So they're in the right order to have a reaction. So we will get a reaction between iron and the nickel and cadmium hydroxides. We won't get any reactions with the copper, the lead, the tin, and especially with the potassium, because it's way on the wrong-hand side. If this was potassium, the metal, its electrons would be so ready to jump off, would pretty much react with anything. But this is already a hydroxyl group, so it's already let go of its electrons. So forget about potassium hydroxide causing any problems at all with battery leaks on these boards. It's just not going to happen. So iron, what happens is the solid iron has some electrons on the surface, and they're like, oh, I sort of want to jump off, but I need to, like, I need somewhere to go. And then the nickel and cadmium hydroxide ions come along, and the electrons go boom and jump off and land on these guys. And then we get a reaction. And so iron then frees itself from the solid, and we go have all hell break loose. Right, so enough of me postulating, because I'm probably wrong anyway. Let's fix the board. So, wow, one of the biggest problems on boards like this is that the resistors aren't labelled. So you have to trace each resistor via the track, if the track's still there, which they are, because it's mostly just copper. So we can trace the track from the resistor to the pins on the ICs, and then we can use that to find out what the resistor value is on the schematic. So each of these resistors, I just measured which pin they went to on the IC, and then from the schematic worked out what they were. So I just have to continue to do that with these other resistors, and on some of the capacitors that don't look that great. This part here has been affected on the outside of the package, but the inside's okay. This is actually a line filter, so it's two inductors and a capacitor. There's another one up here where the outer package hasn't reacted, but internally it's fine. So I'm just going to leave that there. But all the resistors have to go, and it needs a new battery and fix these pads. It can be really difficult finding out what value the resistors are, especially if the legs are really rusty. Sometimes, these ones are not too bad, but sometimes you can't even get a measurement through the legs because the rust is so bad that you just get no connection at all. And the schematic depends on the synth, but the schematic can be really bad as well. It can be quite difficult to read. Depends on how well they're scanned. But there's a really neat trick to find out what value the resistors were, and that's you can just snap the legs off where the rust is and measure end cap to end cap. So once you snap the legs off, you've still got the metal end caps encapsulating the resistance. So if you just press your probes tightly on the end, you should be able to get a value. See, that's 180k. And I knew that because I could still read the bands on the resistor. But it's a really neat trick. In case you get stuck, just get some pliers and snap the legs off, and most of the time you'll still have the metal end caps present, so you can still measure it. Okay, so the board's been repaired and it's actually working, which is awesome. You'll notice one thing is that the battery's not in yet, and that's because when I repair synths with battery leaks or memory problems, I usually don't put the battery in until I'm sure it's actually working, because you don't need the battery to store patches. You only need the battery to remember patches once the synth is off. So when the synth is on, this is not needed. And it allows you to test the circuit around the battery, make sure that the voltage that's going to it won't blow it up, make sure it's charging properly, all that kind of stuff. So the original problem with the synth was that we weren't storing patches. So it had something to do with these 4 chips here. So these are the static RAM chips. They're actually a 2K by 8, so a 16K static RAM. And there's 4 of them that we store our data in. So it had to be something to do with the battery leak causing rust or something to not work around this area. So when we're storing patches, we're basically just taking data from the CPU. Then the CPU has a whole lot of address lines that come out. They actually go through this chip here, and they address the ROM and the RAM. And so our memory address comes through here. And then there's a couple of chips here which select which RAM chip is active at the time. So these 2 chips control or go to the chip select pin, which is pin 18 on these static RAM, and they will select or deselect a single one that then the address lines refer to, and then the data comes in. So we knew the fault was somewhere around there. So I've firstly gone through and replaced all the components that I could see that were visually damaged or that I couldn't get any readings on with my probe. So I would put the probe on, and if I couldn't get a reading across the resistor, I'd just pull it out, replace it. And that involved, as I said before, the first thing was to put the circuit board under really hot water with a toothbrush, get rid of all the solder mask that was all sticky. And then once that was off, then it was just a matter of getting the components out. And that's the really hard bit, because the solder doesn't quite, or it doesn't have the same melting point as before. So I got the biggest solder tip that I had, and fairly hot, and I just scraped across the pad. So once the components were out, I scraped the rust off with a hot soldering iron as much as I could, just to start it off. And then I came in with the isopropanol and the Q-tips. I used about 50 of these. And scrubs with isopropanol. And then I got sandpaper out and then sanded it back until it looked like nice and shiny. And then I would clean the sanding up with more isopropanol. And I would repeat that process enough times so that the pads looked nice. And put the new components in, including the chips that did the chip select for the RAM and the chip that handled the address assignment. And then I put it in the synth and tried it out. And guess what? It didn't work. So that's okay. Quite often when you do a visual repair and then you test the board, it may not work afterwards, but you need to do it because there's a lot of rust around. You can't just leave it like that. So now that I replaced all the components and everything looked good, it was time to do the real troubleshooting. Now, when I first replaced the components, I didn't actually replace these capacitors here. They have a really important function. Is that they're like the local storage caps that store power for the chips. Digital chips have quite high inrush currents because all the transistors inside tend to switch at the same time when it's doing something. What that means is when they're actually in use, they could draw sudden amounts of power which drain power out of the copper tracks because there's not much current that can store in these tracks. So if one of these chips gets active around that area, it could draw all the power out of the track and there'll be nothing left for another chip. And what was happening was that this capacitor here wasn't connected. So if you look, sorry, I'm not holding the camera very steady, but this capacitor here wasn't connected, and that was causing this chip to stall. So when it needed power, all of a sudden, the sudden inrush currents couldn't be provided by the circuits around the chip. So it really did need this capacitor to provide the power for it, and it wasn't connected. So when it needed the power, it would run out and it would stall. So I found that if I redid this or put a new capacitor in here and made sure the connections were good, this chip came to life again, our address lines were good, and then suddenly we started saving patches. So now that I know it's working, I can actually go and get a battery and put it in. And there's one other thing left on this board, and that's the copper still exposed. So eventually with the moisture in the air, those tracks will tarnish. It's probably not a good idea. So I'm going to recoat it with some new solder mask, which I found off eBay in China. So it's over here. I can't read it, but it's UV something. But the inside is green. So at least it's the right color. So, okay, well, I guess I'll try that out, put it in the sun. I've never used that before, actually. Okay, so finally we're up to the battery. I get to put the battery back in, which is excellent. We'll be able to save patches when the synth is off. Obviously, this is not rechargeable. I'm not using the original. They're quite hard to find now, and also, eventually they would leak again. So a lot of people now replace them with dry cells. It's quite common to do this, to replace your rechargeable with a non-rechargeable battery. The only trick is that you need to add a diode, because we don't want this battery to charge. So when the synth is on normally, there will be positive charge that's slightly higher than the battery voltage coming in here to recharge, but we don't want that to happen now. So we need to put the diode here to block that incoming voltage so that it can't get to the battery. The diode still allows charge to come out of the battery when the synth is off, but it doesn't allow charge to come in when the synth is on. So on the positive terminal, you need to have the positive part of the diode connected. So usually the triangle part's positive and the line is the negative. So positive to positive, and that allows positive charges to come out. And hopefully save our patches. So I'm going to put shrink tube on that now, finish it off, install it in the circuit, and then find somewhere in the synthesizer to place it. And then we'll have a play with the synth, because it's a really great synth. I like the SX240. It's quite a decent DCO synth. It's pretty cool. And last of all, the solder mask. I hope this works. I really hope this works. Usually I just paint it or put lacquer on or something, but... And then after I put this on, all I have to do is put it in the sun to dry, and it should harden up and protect the copper. And we're done. Yes, the battery's in and it's saving patches now. I've put glue over the bottom of the pin so it doesn't short out, but I'll need to tape that up and secure it somewhere. The solder mask dried really well. It's not exactly the same colour green, but no, it's not too bad. It's better than the stuff I used to use before. And let's confirm that we still have patches. Yes! If it doesn't, it'll say basic to like this. Hang on, let's get a patch. Yeah, basic 240, that's what turns up when you're not pulling anything from RAM. So that's the default. So we've got patches, which is brilliant. Love this synth. It's a nice synth. We're in dual at the moment. So stab, let's add a stab. Yeah, I like adding stabs to strings. Nice, nice. Love this synth. Okay, so we're done, and I hope you enjoyed this one. I certainly didn't. There was so much work on the board. Just getting that rust off was horrible. Yeah, but it turned out well. Hopefully my predictions about the legs on the IC pins and the capacitors and the metals involved and why they rust, I hope that's right. If it's not, then maybe we'll find out. Maybe someone will put the correct answer in the comments. If not, then cool. So what's next? There's a few synths coming up. I'm not exactly sure what I'm going to do next. I have a CS60 that I need to recap. I still have the OBX to do, and I'm hoping for an MS-20 too. That'd be fun. So until then, thanks for watching.